Hello everyone, my name is Ben Shriver. Here's my partner and good friend Yikai Wang.
Hi everyone, I'm Yikai, Ben's partner on this project.
And together we wrote a paper called Creating a Traffic Merging Behavior Using NeuroEvolution Augmenting Topologies. Now what this means is we've essentially trained a neural network or brain using this approach called NEAT to create a traffic behaving car. So a car that can learn how to merge into the traffic lane from an exit lane using this sort of approach. So we're going to show you how we did it. So again, our goal here in this project is to create a behavior that knows how to merge onto the highway using neural evolution augmenting topologies, otherwise known as NEAT. So here's the environment where we run this experiment. We have a agent, the blue car, that's trying to get into the upper lane of traffic. So we have some red cars moving at a steady pace, each with the same amount of space in between them, and we want our blue car to make it to the star. Before we start talking about NEAT, it's important to understand a few things about a neural network. You can think of a neural network as a formula that takes in certain inputs from the environment and outputs either a classification or behavior. This formula can actually be visualized as a graph architecture where the inputs form a layer of nodes, and each node will have connections to other nodes in the next layer. Now these connections all have corresponding weights, and each node in the next layer will take a linear combination of the inputs times their corresponding weights and sum this up and pass the sum through an activation function. You can think of this function as something that just tells the neuron how on or off it needs to be. Now, this process can occur over many layers, or it can happen over just a single layer, as we see here. But the point is, once you eventually reach this output layer, the final two nodes, or however many nodes are in your output layer, can be interpreted as a classification or decision. So before we talk about NEAT, it's also important to understand what a genetic algorithm is. We start with a randomly spawned generation of candidate solutions to a particular problem, and we're going to repeat the following steps many times. So we're going to test each candidate based on some prescribed fitness measure in a test environment. Next, we're going to randomly select individual candidates to mate, favoring candidates with higher fitness. Now, the offspring will carry on to the next generation. And before we carry them on, we also may or may not mutate them. So we'll change their structures a little bit. And after this is all done, the offspring from this generation will become the candidate solutions for the next generation. So we're going to continue this over many, many repetitions, and eventually we'll wind up with some pretty good candidate solutions. So now that you have a general understanding of neural networks and genetic algorithms, we can discuss NEAT. So NEAT itself is a genetic algorithm where the candidate solutions are actually neural networks. This method here was created by Kenneth O. Stanley and Risto Mikalainen at the University of Texas. And what's special about this method is that first, it fosters diversity, so you're going to get a lot of different looking topologies in your final generation of solutions, and it encourages simple topologies and networks, which is going to enhance the efficiency of the evolution. So how does this work? How do the mutations occur in NEAT? One way is by changing edge weights. Another way is to insert new edges or insert new nodes. So I gave an example here of how to insert a new edge. So here you can see there's no edge between this node and this node, but after a mutation, there is. Our hypothesis for applying NEAT to creating a behavior to merge onto the highway is that it will at least beat the initial population. So the best individual in the final population of NEAT will be better than the best individual in the randomly created initial generation. So how do we rate the quality of a solution? Well, first, an agent maximizes its fitness by reaching the top right portion of the screen without oscillating, as we see here, through the lanes and without crashing. So you can see this guy crashed here. And normally, if it doesn't finish, we would just say that the fitness is a function of its final X position. So if this guy were to finish his test run and he's only here, we would say, okay, your fitness is just some function of your X position. However, if you crash, then we're going to divide that X position by 2. Also, we favor agents who finish faster than others. So if you do make it to the final goal place, then if you finish faster, you're better than another solution that made it to the goal place but slower. So to this network, we're going to feed in 7 different inputs. One is the speed of the traffic cars. Another is the X distance to the nearest car behind, X distance to the nearest car in front, the agent's current XY position, and its current speed and heading.
Now, in this environment, the traffic cars are not evenly spaced, but you should know that in the test environment, they are.
The outputs of our neural network are going to be acceleration, which ranges from -1 to 1, so it can decelerate as well as accelerate, and rotation, which will also be from -1 to 1. So you can think of our neural network as having 7 of those input nodes, which have the fields described in the previous slide, and 2 output nodes with these particular fields. Our first experiment was seeing if NEAT could evolve an agent that would learn how to merge when the frequency of traffic was 1 new car per 50 time steps, where time steps are the unit of time in the simulated environment. And 1 car per 50 time steps we decided empirically was more than enough room to merge. And as expected, our results were pretty good. You can see that by around generation within 25 and 30, we've already found an optimal behavior. And we even find a faster one around here. And you can also see that the average fitness increases steadily throughout many generations of NEAT.
So this guy here was trained on 50, and as you can see, he merges pretty comfortably at a level of 1 car per 50 time steps. And no, he's not touching the other car.
So after succeeding on the environment where we have frequency of 1 new traffic car per 50 time steps, we wanted to see if we could ramp up the frequency so that the agent doesn't have so much room in between traffic cars to merge. So we tried 1 car per every 20 time steps. And you can see here that NEAT also did really well. So you can see by around, generation 15, it's already found an optimal behavior that reaches the goal.
So here we see traffic at a rate of 1 car per 20 time steps, and the agent fits in very smoothly to this intense flow of traffic.
Now, there was actually a limitation in this last experiment in that we expected it to be able to, in addition performing well on the frequency of 1 car per every 20 time steps, to perform well on less intense frequencies. But it actually didn't do well on other frequencies, even if they were less intense than what it was trained on. So this agent essentially does not adapt to new environments. It only can succeed in the one it was trained. Here's what I mean by that.
These 2 graphs here are the best individual from the first generation and the best individual from the 100th generation. And they're tested across multiple frequencies, that is, integer frequencies between 10 and 80. And we can see that the initial generation is awful.
The fitnesses here do not grow at all as we increase the frequency of traffic, so no matter what, the initial generation is bad. However, after we've trained for 100 generations, we can see that the individual will succeed at a frequency of about 20, so 1 car per every 20 time steps. But if we give it a less intense frequency, its fitness is horrible.
So here traffic's moving at a rate of 1 car per 70 time steps, and the agent has no idea what to do.
In experiment 3, our goal was incorporating adaptability on the frequency of traffic. So as long as it's possible. Sometimes the traffic is just too heavy to merge. Instead of training on just a single round, so a single environment per generation of evolution, we actually trained on multiple environments per generation of evolution. We trained on a frequency of 1 car per 20 time steps, 1 car per 30 time steps, 1 car per 40 time steps, and 1 car per 50 time steps. We took the fitnesses of each one of those runs and averaged them together to give an agent a fitness for that specific generation.
Neat did find an agent who was able to succeed on all 4 of the environments. It took a little longer this time. You can see by about generation 45 it's found an optimal agent.
But wait, there's even more. So, in addition to being able to succeed on environments where the frequency of traffic is 1 car per 20 time steps, 30 time steps, 40 time steps,
And
50 time steps, the agent actually merges successfully for any integer frequency between 1 new car per 70 time steps to 80 time steps, and possibly beyond 80. We didn't even test beyond that. So we have essentially achieved adaptability over a single variable. And here's what I mean by that. So you can see here, obviously the initial population is very bad, but when we train after 100 generations on multiple rounds per generation, we can see that the agent succeeds on all of these different frequencies.
here, this agent was trained on 4 different environments where there was 1 car per 50 time steps, 40 time steps, 30 time steps, and 20 time steps. This is it succeeding on an environment with 1 car per 50 time steps. Here we see the same exact agent perform well on an environment with 1 car per 20 time steps, so the frequency is much different than the previous environment you just saw. Here's an instance of the agent succeeding on an environment in which it was not trained. Here cars are coming at 1 per every 35 time steps, and this shows that it is adaptable. It can adjust itself to new situations. So this is the best neural network created by NEAT after evolving for 100 generations. So you can see that the input nodes are the gray squares at the top. The outputs, acceleration and rotation, are the blue circles at the bottom, and all the nodes in between are results of mutations. So this is what we were able to achieve in just over a month, and there are obviously still many remaining objectives. This is far from a vehicle that could survive on the road, but I thank you for watching what we have completed so far, and maybe we will continue to embark on this.